Welcome students. We are back with another lesson. Now in this lesson we'll continue with the experimental study of your photoelectric effect. So up till now we have discussed the effect of the intensity of light. How does your intensity of light affects the photoelectric current? Then we have discussed the effect of potential. How does increasing the potential affects your photoelectric current? How does decreasing your potential affects the photoelectric current? And then we had discussed about the stopping potential, the potential required to stop this photoelectron from emission. And then we have plotted the curve between the photocurrent and your potential for various intensities like I1, I2, I3. Now in today's class we'll see how the frequency of the incident light affects the current. So suppose you have a source of light. This source of light emits a radiation of small frequency. Now let us suppose this source is producing a light of low frequency. It is radiating a radiation of low frequency on this photosensitive plate. What happens? The photoelectrons are emitted. So if the radiation falls, the photoelectrons are emitted. These photoelectrons are detected by your ammeter. So this is what you'll get. As you increase the potential, the photocurrent also increases. It increases till you reach a constant value. This part. This constant value of the current is known as your saturation current. Now what you do? You start decreasing the potential. So if you start decreasing the potential, what happens? The photocurrent also decreases. Now you decrease it further till you reach the stopping potential V01. So at stopping potential V01, what happens? The photocurrent reduces 0. That means no photoelectrons will be emitted from here. Fine. So V01 represents your stopping potential. Fine. This is for your frequency, let us say mu1. Fine. Next what we'll do, we'll replace the source of light with another radiation of another color, of another frequency, which will be higher than this frequency. Fine. Fine. So we radiate this photosensitive plate with another radiation of frequency mu2. Then the photoelectrons are generated, and in turn you will notice some current at this ammeter. Fine. Now let us increase the potential. Now if you start increasing the potential, what happens? The photoelectron generated will be more, therefore more currents will be detected. So again the current will increase. The current will increase up till it reaches a constant value of current. Can you see this green line? This green line shows, or let me represent with yellow line, okay, because since it is a yellow color light. Okay, fine. So this represents your increase in the photocurrent with the increase in the anode potential. So the current increases with the potential till it reaches a constant value. We will maintain our same saturation current, okay, for your frequency mu1. This red radiation for the red source of light will maintain the same saturation current for this yellow source of light. Fine. So the saturation current is same in both the case. Fine. Now we have attained the saturation current. Now what we will do is we will again start to decrease the potential. Now if I start to decrease the potential, this one, what happens to the photocurrent? The photocurrent also decreases. Fine. Similarly, a further decrease so that your anode potential becomes 0. That time what happened? Your photocurrent decreases further when this potential becomes 0. Now we will start to apply retarding potential. Now if I start to apply this retarding potential, what happens? The photocurrent decreases further. Now what happens at a particular value of this potential? Let us say at V02. At this potential, what happens? The photoelectric current becomes completely 0. That means no photoelectron should be emitted. Fine. So this V02 is the stopping potential for the radiation of frequency mu2. Fine. So let me show this in the graph. So your curve will look somewhat like this for your frequency mu2. This frequency mu2 is greater than your frequency mu1. And what you notice, the stopping potential of this yellow color radiation is more than the stopping potential of this red color radiation. Right? Now let us repeat this experiment one more time, but for another color, for another frequency which is higher than mu1, higher than mu2. Now let us suppose we radiate this photosensitive plate with radiation, this blue color radiation. This blue color radiation has a frequency higher than this two radiation. Fine. Now when the radiation falls on this plate, what happens? The photoelectrons are emitted. So if photoelectrons are emitted, photocurrents are generated. Fine. Now you apply the voltage here, you start to increase the voltage here. So if you apply the voltage and start to increase the voltage, what happens? The photocurrent increases, and the photocurrent increases until you reach a saturation current, until you reach a constant value of current, which is known as your saturation current. Again, we will maintain our apparatus in such a manner that we get a same saturation current. Fine. So this is how the curve will look. So at this point you have zero anode potential. The photoelectrons are emitted only due to the radiations. Fine. Now what happens at this part of this curve? What happens? You start to apply this anode potential. When you apply this anode potential, the potential increases across the circuit, which in turn the potential increases across this plate. By circuit means across this plate. By increasing the potential across these plates, what happens? More photoelectrons are emitted and more current will be detected. So what happens? You see a small linear portion. Fine, this part. Now as you keep on increasing the potential, what happens? At a particular potential, like beyond the particular potential, what happens? Your saturation current will become constant. That's why you see this straight line curve. What happens? The saturation current become constant. That means no matter how much you increase your potential further, the saturation current will always be remain constant. This part. That's why it is known as your saturation current, the maximum value of the current. Fine. Now again what we will do? We'll start reducing the potential. What happens? The current will also starts to decrease and it will reduce to 0. The point at which it reduced to 0 is known as the stopping potential for the frequency mu3. So at your stopping potential V03, what happens? The photocurrent reduces to 0. That means no photoelectrons will be emitted in this case. Right? So this is how the curve will look like. So this is for your frequency mu1, this is for your frequency mu2, and this is for your frequency mu3. And this is the order of the frequency. The frequency of this blue color is the highest, the yellow color is medium, and the red color is the smallest. Fine. Now can you see the stopping potential? Look at the stopping potential also. For small frequency you get small stopping potential, for medium frequency you got medium stopping potential, for high frequency you got high stopping potential. So there is a relation between the stopping potential and the frequency. Fine. The stopping potential depends on the frequency. If frequency increases, the stopping potential also increases. So if we plot a curve between your stopping potential and your frequency, stopping potential will plot along y-axis and the frequency will plot along x-axis. So if we plot a graph, what we'll note is that we will get a curve similar like this one. In this curve, what you note is that if you increase the frequency, the stopping potential also increases. Therefore, you get a linear curve. Fine. This is what has been observed in the photoelectric effect. But in this curve, look at this point. Let us name this point as mu0. Fine. Now at this point, what you notice is that you have a light which is coming with the frequency mu0. And at this point, what is the stopping potential? The stopping potential is 0. Okay, let me just show this with the diagram. So according to this curve, suppose you have a frequency coming. This frequency, let us say mu. If you have a frequency coming mu, then what happens? The photoelectrons are emitted. Fine. And in order to stop this photoelectrons, what do? You apply a stopping potential here. So if you apply stopping potential here, what happens? No photoelectrons should be generated here. If no photoelectrons are generated, that means no current should be detected. Fine. So the stopping potential depends upon the frequency. Higher the frequency, higher the stopping potential. Lower the frequency, lower the stopping potential. So this is shown by this part of the curve. Fine. Now look here at the frequency mu0. Fine. Now let us apply a frequency mu0. So after applying a frequency mu0, okay, even after applying the radiation, okay, without the stopping potential, even after applying the radiation, okay, just forget about this stopping potential for now. So even after applying the radiation, no photoelectrons are emitted. No photoelectrons are emitted. If no photoelectrons are emitted, that means it's not required to apply a stopping potential here. So without stopping potential, I have reduced the current to how much? 0, since no photoelectrons are emitted. So from this, what you can conclude? We can say that if the radiation is of frequency mu0, no photoelectrons are emitted. Similarly, if the frequency is less than mu0, then in that case also no photoelectrons will be emitted. That means the stopping potential is 0. Fine. No photoelectrons are emitted, so no stopping potential needs to be applied. So the stopping potential is 0 for V0. Fine. So this V0 is known as your threshold frequency. Threshold frequency means the frequency above which the photoelectrons will be emitted, and the frequency below which, or at the frequency or at your threshold frequency, no photoelectrons are emitted. Therefore, in order to observe this photoelectric effect, the frequency should always be greater than your threshold frequency. So let's discuss the effect of frequency. For a given photosensitive material, there exists a minimum cutoff frequency. This is your minimum cutoff frequency. Below this frequency, no photoelectrons are emitted, howsoever high be the intensity of the incident radiation. That means no matter how much be the intensity of the incident radiation, no photoelectrons will be emitted unless and until the frequency is greater than mu 0. Fine. This is your first point. Now the second point is above the threshold frequency. Above this threshold frequency, that means this part. Above the threshold frequency, the stopping potential or the maximum kinetic energy of the photoelectrons. The stopping potential, okay, which is also equal to the maximum kinetic energy, which I've showed here. The stopping potential is equal to the kinetic energy of the maximum velocity. This stopping potential is equal to the electron having the maximum velocity, therefore maximum kinetic energy. So this stopping potential and the kinetic energy are equal. Fine. So above the threshold frequency, the stopping potential or equivalently the maximum kinetic energy of the photoelectron is directly proportional to the frequency of the incident radiation. Fine. So above this threshold frequency, what you notice is that as the frequency increases, the stopping potential also increases. Fine. So it is directly proportional to the frequency of incident radiation, but is independent of the intensity. No matter whatever be the intensity, you will see the same curve. Fine. So why is it so that no whatever be the intensity, okay, why is it is independent of the intensity? Like if you have more intensity, that means more photoelectrons should be emitted. More photoelectrons emitted, more current should be detected. More current detected, more stopping potential. But why is it independent of the intensity? Okay, this is the first question. The second question is, if the light of the radiation has some frequency, if this has some frequency, why is it that no photoelectrons are emitted? If it has some frequency, that means it has some energy. If it has some energy, then it should emit some photoelectron. If it should emit a photoelectron, that means it should detect some photocurrent. Why is it not detecting any photocurrent? Okay, these are some failures of this photoelectric effect. Okay, this failures will be explained by Einstein in the Einstein's theory of photoelectric effect, which we will discuss in our next class. Fine. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I will re-explain it to you again. So again, thank you.